the heart of North America rises a colossal spine of stone. The Rocky Mountains stretch for thousands of miles, their jagged peaks slicing through clouds like the bones of a sleeping giant pushing against the sky. But beneath their majestic calm lies a story that spans hundreds of millions of years, a story of unimaginable collisions, shifting plates, and forces powerful enough to tear a continent in two. Far beyond Earth, at the frozen edge of our solar system, another mystery lingers. Pluto, once the ninth planet, now reclassified as a dwarf, hides secrets beneath its icy shell. Strange geysers, a vanishing atmosphere, perhaps even an ancient ocean. Its journey mirrors our own planet's geological drama, but in the silence of deep space. And above us, unseen but omnipresent, is Earth's fragile, invisible shield, the atmosphere. It sustains every breath, shields us from lethal radiation, and shapes the surface we walk on. But how did this delicate layer survive when others, like Mars, were stripped bare? And what role did cosmic accidents and distant icy worlds play in creating it? This is a story about foundations, both visible and hidden. From mountain roots buried miles beneath North America to a faint layer of air that keeps us alive, from the birth of continents to the frozen frontier of Pluto, the same physical forces bind them all. Across 12 to 15 parts, we will journey through time and space, back 200 million years to the violent birth of the Rockies, out 3 billion miles to Pluto's shifting atmosphere and ancient ice, and upward into the stratified layers of Earth's protective veil. We will follow geologists unearthing fossils of sea creatures high above the ground, astronomers tracing faint points of light across the night sky, and scientists ascending into the thin upper reaches of our atmosphere. Along the way, one question echoes: can the same forces that built mountains and sculpted planets also decide the fate of entire worlds? If the Rockies are North America's backbone, Pluto is the memory of the solar system's youth, and the atmosphere is our shield. But none of them are eternal. The Rockies are eroding, Pluto is shrinking, and the atmosphere is under threat. Their fates are intertwined with forces far larger than ourselves, forces that continue to shape not just landscapes, but destinies. Welcome to The Bones of the Continent. Part 1, The First Clues Beneath the Peaks. The story begins not on a mountain summit, but at its base, in Yoho National Park, British Columbia, where walls of ancient rock reveal a puzzle that defies intuition. High on Mount Stephen, at nearly 8,000 feet above sea level, geologist Paul McNeil brushes the surface of a limestone cliff and uncovers the imprint of a creature that should never have been there. Embedded in the rock are the delicate spines of hallucigenia, the bizarre, worm-like animal with legs sprouting from its back. Next to it, the soft outlines of Wawaxia shimmer under the mountain light, fossils so fragile they look as though they could crumble into dust at a touch. These are not mountain dwellers. They are the remains of organisms that once lived on the floor of a shallow tropical sea over 500 million years ago. How could creatures that once swam near the equator, in warm shallow waters, end up entombed in rock at the top of a mountain range thousands of feet above the present sea? The fossils are a message from another world, one that existed long before there were mountains here. 200 million years ago, there were no Rockies. North America itself was part of a vast supercontinent known as Pangaea, a single sprawling landmass. But beneath the calm surface of this ancient Earth, immense forces were gathering. Deep inside the mantle, slow convection currents stirred like boiling water beneath a crust of cooling bread. These currents would one day rip Pangaea apart, sending its fragments drifting like rafts across a global ocean. As these continental rafts began to separate, the western edge of what would become North America lay submerged beneath a shallow sea. Layer after layer of mud, clay, and gravel settled on the seafloor, trapping and fossilizing countless marine creatures. Over millions of years, these sediments hardened into rock up to 12 miles thick. The fossils on Mount Stephen were buried 6 miles beneath the surface, compressed and entombed beneath relentless geological pressure. For most of human history, no one suspected this ancient seabed existed. To early explorers, the Rockies seemed eternal, their jagged ridges and snow-capped peaks symbols of immovable permanence. But in the late 19th and early 20th centuries, geologists began mapping the layers of rock across western Canada and noticed something unsettling. The layers were upside down. Older rocks lay on top of younger ones, folded and shoved eastward as though someone had taken a massive rug and pushed it from one end until it wrinkled. This observation was the first clue that something far larger than erosion or simple uplift had taken place. These were not ordinary hills formed by local buckling. They were the surface expression of a continental-scale collision. When the first fossil excavations on Mount Stephen gained international attention in the early 20th century, the scientific community was both thrilled and baffled. Newspapers reported sea creatures found in the sky. Museum displays struggled to explain the paradox. How could tropical seabeds be perched atop mountains in a temperate interior? The answer, as geologists would soon discover, involved not just the movement of land but the collision of entire plates of the Earth's crust. It was a story of subduction, one plate plunging beneath another, and of ancient islands being crumpled into a continental margin like cars in a slow-motion pile-up. At the time, plate tectonics as a theory had not yet taken shape. These observations were fragments of a puzzle that would take decades to assemble. But already, the evidence on the cliff face at Mount Stephen hinted at a process vast enough to move oceans and build mountains out of seabeds. Meanwhile, outside scientific circles, these discoveries stirred public fascination. The idea that mountains had once been underwater captured imaginations. Teachers began using fossil seashells found in alpine rocks as tangible proof of Earth's ancient past. Photographs of delicate Burgess shale fossils circulated through academic journals in Europe, sparking debate about evolution, paleogeography, and the age of the planet itself. The Rockies, it seemed, were not just towering ridges of stone. They were archives, geological libraries storing pages from Earth's deep history, waiting to be read. And the fossils high above Yoho National Park were the opening chapter. Part 2, when continents began to tear apart. Roughly 200 million years ago, the supercontinent Pangaea stood as the most immense landmass the planet had ever known. From pole to pole, its coastlines wrapped the Earth like the single shell of a colossal egg. Yet even in its apparent stability, fractures had begun to form deep below the surface. The mantle, the vast layer of hot, slowly flowing rock beneath the crust, was in constant motion. Convection currents, driven by the gradual cooling of the planet's interior, pressed relentlessly against the underside of Pangaea's shell. Over millions of years, this pressure built up like steam trapped beneath a sealed lid. Eventually, cracks began to appear along weak zones in the crust. Geologists can now trace these cracks with remarkable precision. What began as faint rift valleys in the Triassic period widened into gaping chasms during the Jurassic. Molten rock surged upward through the fractures, forcing the continental plates to drift apart. As the Atlantic Ocean opened, the western edge of what would become North America was pushed outward over the deepening basin of the Pacific. At this stage, the western coast of North America was a low, submerged continental shelf, a vast shallow sea teeming with life. Layer upon layer of sediment accumulated across its breadth, entombing marine creatures that would one day be found fossilized high above modern forests. But as the plates diverged in the east, something else was happening in the west. The Pacific Ocean plate, denser and heavier, began to move eastward. North America, freshly detached from Pangaea, was drifting westward. Their inevitable collision would set in motion one of the most powerful geological events on Earth: subduction. Modern simulations show this process as two slow but unstoppable masses converging. The Pacific Plate, like a conveyor belt loaded with islands and sediments, was forced downward beneath the buoyant continental crust of North America. It sank into the mantle at an angle, dragging everything on its back into the collision zone. Offshore island arcs, chains of volcanic islands built on oceanic crust, were carried toward the continent by this relentless conveyor. When one particularly massive island reached the edge of North America about 180 million years ago, It refused to be dragged beneath. It was too thick, too buoyant. Instead, it slammed into the continental shelf. The result was cataclysmic, though it unfolded over millions of years. The seabed was thrust eastward, crumpling like a rug pushed against a wall. Layers of sediment that had once lain flat on the ocean floor folded upward, stacking on top of each other and sliding inland. In time, these folds would become the Northern Rockies. At the time, there were no humans to witness this slow collision, but its effects were recorded in the rocks themselves. Horizontal layers bent into great arcs. Thick slabs sheared along thrust faults, older layers sliding over younger ones. Limestone that had formed under tropical seas was lifted thousands of feet into the air. When geologists in the 20th century began to map these formations systematically, their reaction bordered on disbelief. "It's as if the continent itself was shoved from beneath," wrote one Canadian geologist in a 1930 field journal. Older rocks ride above the younger like pages of a book torn loose and rearranged. These early observations predated the formal acceptance of plate tectonic theory by decades. Scientists relied on stratigraphic mapping, fossil dating, and structural measurements to make sense of the evidence. Some argued for local buckling, others for catastrophic uplift. But none of those explanations could account for the scale and order of the deformation. It wasn't until the mid-20th century, with the development of plate tectonic theory and seafloor spreading data from the Atlantic, that these observations snapped into focus. The Rockies were not an isolated anomaly. They were part of a global system, the direct consequence of plate collisions on a continental scale. Meanwhile, as these scientific debates unfolded, the mountains themselves became symbols in the public imagination. Artists painted them as eternal sentinels. Travelers wrote of their overwhelming grandeur, never suspecting that the peaks were once ocean floors, shoved inland and skyward. By the time this realization entered textbooks in the latter half of the 20th century, it fundamentally changed how people understood Earth. Mountains were not static features but dynamic records of planetary movement. The Rockies were no longer just a scenic backdrop, they were evidence. And beneath them, the process that had begun with the rifting of Pangaea continued its slow, inexorable march. Plates were still converging. Forces were still building. The continent's fate was still being written in stone. Part 3: The Collision Zone. As the Pacific and North American plates inched toward each other over tens of millions of years, the western edge of the continent transformed into a slow-motion collision zone of staggering power. Imagine two vast rafts drifting on a molten sea, meeting head-on. One raft is lighter, it rides high. The other is denser, it dives below. This is the essence of subduction. About 180 million years ago, the dense Pacific Ocean plate began to plunge beneath the North American plate. Along the western continental margin, entire slabs of ocean crust disappeared into the mantle, like a conveyor belt feeding rock into the interior of the planet. The descending plate carried volcanic island chains and sediments toward the continental shelf, pressing them against its edge. When a particularly large island arc reached the margin, the collision was too much for the subduction zone to absorb. Instead of sliding downward, the island smashed into the continent's edge. The seabed itself was shoved eastward, folding and stacking as if a rug had been pushed into a wall. Geologists call this process thrust faulting, when enormous slabs of rock break along plains and are pushed up and over one another. In the Canadian Rockies, thrust faults can extend for miles, stacking older rock atop younger rock in dramatic defiance of the normal geological order. Ben Gadd, a geologist who spent decades studying these formations in British Columbia, often explained the process with his hands. "Think of the bones of your hand," he'd say, holding up his palm. "The bones are the rigid continental crust. The skin on top is the sedimentary layers. Now push from one end. See how the skin wrinkles and slides over the bones? That's how the Rockies formed. The evidence is written across the landscape. Jagged peaks and horizontal bands of sedimentary rock reveal the mechanics of thrusting with eerie clarity. In Yoho National Park, some thrust sheets are more than a mile thick, having been pushed tens of miles inland. Rocks that once lay beneath the sea now form towering cliffs more than 2 kilometers above modern sea level. In the early to mid-20th century, field geologists working in the Canadian Rockies struggled to map these structures. They hiked through valleys, climbed ridges, and hammered at outcrops to decipher the complex layering. At first, the patterns seemed chaotic. Older formations atop younger, layers repeated or missing altogether, entire sections displaced sideways. It wasn't until structural geology advanced, aided by aerial photography, seismic surveys, and later satellite imagery, that the scale of the deformation became clear. These were not local faults. This was an entire belt of the continent crumpled like paper. Thrust faulting began in the west and progressively shifted eastward over tens of millions of years. First the western ranges rose, then the main ranges, and finally the front ranges, each wave representing another pulse of compression as land was shoved inland. By 85 million years ago, the final thrust sheets had reached the plains, where the jagged mountains meet the flat lands of Alberta and Montana. Throughout this time, erosion was relentless. As the mountains rose, rivers and glaciers immediately began wearing them down. In some places, as much as 2 miles of rock were stripped from the summits, carried as silt and sand into distant basins. But thrust faulting had given the Rockies a secret advantage. Deep below the visible peaks, the mountains had roots, thick, buoyant keels of crust extending miles into the mantle. As erosion shaved off the top, the roots rebounded upward, keeping the mountains from collapsing completely. This process, called isostatic uplift, acts like a cork in water. When you shave off the top, the cork bobs upward. Structural geologist Carl Karlstrom of the University of New Mexico likened it to an iceberg. "The mountains you see are just the tip," he explained in a demonstration. "Their roots can be 5 or 6 times deeper than their height." This combination of thrust faulting and isostatic rebound gave the northern Rockies their characteristic sharp peaks and horizontal strata. Unlike many other mountain chains, where layers are tilted or folded into chaotic shapes, the Canadian Rockies preserve their original horizontal bedding even as they tower above the landscape. For scientists, these formations became a natural laboratory, a place where the mechanics of mountain building were exposed in cross-section. Students from around the world came to Yoho, Banff, and Jasper to learn how to read the language of rocks. Each thrust fault, each repeated layer, told a story of collision, compression, and uplift. For the public, however, the grandeur of the Canadian Rockies masked the violence of their birth. To the casual observer, the mountains appeared eternal and serene. But to the geologist, every ridge was evidence of unimaginable forces at work. Forces that had once rearranged the crust of an entire continent. And while the northern Rockies were rising through the combined action of subduction and thrust faulting, farther south, a different story was unfolding. The geology of the American Rockies would take a radically different turn, one that puzzled scientists for decades. Part 4: The Rise of the Granite Mountains. As the Rocky Mountain chain extends southward across the U.S.-Canada border, a subtle but dramatic geological shift unfolds. The landscape of steep, horizontally banded sedimentary ridges carved by thrust faults gradually gives way to a very different kind of terrain. In Montana and Colorado, the familiar limestone and shale strata are interrupted by something ancient and unexpected: granite. This granite is not a surface veneer left by erosion. It is the exposed basement rock of the North American continent itself, 1.7 billion years old, formed deep within Earth's crust long before the first dinosaurs appeared. It rises abruptly among the surrounding sedimentary layers, punching through them like colossal knuckles breaking through a soft crust. For decades, geologists were puzzled by this sudden appearance. Mountain ranges typically form near plate boundaries, where collision and subduction generate the intense compression needed to fold, fault, and uplift rock. But the southern Rockies lie hundreds of miles inland from the nearest plate boundary. By all conventional reasoning, there should have been no mountain building here at all. The key to this mystery lay deep beneath the surface, in the changing behavior of the subducting Pacific Plate. For over 100 million years, The oceanic plate had plunged steeply into the mantle beneath western North America. Then, around 70 million years ago, something extraordinary happened. Instead of continuing its steep descent, the Pacific plate began to slide beneath the continent at a shallow angle, almost horizontal, like a spatula sliding under a pizza crust. This change had far-reaching consequences. As the plate scraped along the base of the continental crust, it transmitted compressional forces far inland, thousands of kilometers from the subduction trench. These forces fractured the ancient continental basement, shattering and uplifting blocks of granite buried beneath layers of sedimentary rock. The result was the formation of the Laramide orogeny, a mountain-building event unlike anything else in North America. Instead of folding and thrusting thin sedimentary layers near the coast, as happened in Canada, the shallow subducting plate shoved up the thick granite core of the continent itself. Red Rocks Park near Denver, Colorado, provides a striking window into this process. There, enormous slabs of 1.7 billion-year-old granite have punched upward through younger layers of red sandstone. Structural geologist Kirk Johnson often demonstrated this uplift using two volunteers to represent the rigid basement rocks, covered by a layer of sediment. As the basement rises, he explained, the overlying layers bend, tilt, and eventually erode away, revealing the ancient granite beneath. Dating this uplift required detective work of a different kind. Geologists turned to the garbage cans of the landscape, the sedimentary basins that flank the mountains. When mountains rise, erosion strips away their surfaces and deposits debris in adjacent lowlands. By analyzing these sediments, fossil pollen, volcanic ash layers, and eroded rock fragments, scientists reconstructed a precise timeline of uplift. Their findings were startling. The Colorado Rockies rose in a geological instant. Just 69 million years ago, the region was covered by a shallow inland sea. By 68 million years ago, perhaps within as little as 200,000 years, the mountains stood tall, their granite cores exposed. For a process that usually spans tens of millions of years, this was astonishingly fast. The shallow-angle subduction model explained several puzzles at once. It accounted for the inland location of the mountains, the presence of uplifted granite, and the lack of extensive folding and thrusting seen farther north. It also showed how a change deep in the mantle could reshape a continent far from its edges. But this was not the end of the story. As the Pacific Plate continued its shallow crawl beneath North America, it eventually began to peel away and sink deeper into the mantle once more. This shift, about 35 million years ago, triggered a new chapter in the Rockies' evolution, one marked not by compression, but by extension, volcanism, and rifting. The land that had been crumpled and shoved upward was now about to be stretched and pulled apart. In the heart of the southern Rockies, a great crack would open in the crust, a feature so vast that, given enough time, it could tear the continent itself in two. Part 5: Cracks in the Continent. By the late Eocene, around 35 million years ago, the immense compressional forces that had shoved the granite heart of the continent skyward began to wane. Deep beneath the southern Rockies, the subducting Pacific Plate, once gliding at a shallow angle beneath North America, abruptly peeled away and plunged deeper into the mantle. This change set off a chain reaction that would alter the landscape in profound and unexpected ways. As the plate sank, it left behind a void that allowed hot mantle material to rise upward, like air rushing in to fill the space beneath a lifted rug. This upwelling mantle brought heat closer to the crust, weakening it and setting the stage for a new phase of geologic activity: extension. Rather than being squeezed, the crust began to stretch. Slowly but inexorably, this stretching opened a vast linear wound across the landscape, the Rio Grande Rift. Extending from central Colorado down through New Mexico, the rift is a scar that cuts through the heart of the Rockies, a sign that the continent is being pulled apart from within. Geophysical surveys reveal the magnitude of this transformation. Seismic imaging shows that beneath the rift, the crust has thinned dramatically, from more than 30 miles thick in adjacent regions to as little as 17 miles in places. Magnetic and gravity measurements confirm that dense mantle rocks have moved upward, bringing geothermal energy close to the surface. In New Mexico, geothermal springs trace the rift like beads on a necklace. Geologist Laura Crossi and structural geologist Carl Karlstrom have spent decades sampling these springs, analyzing the gases bubbling up from deep underground. Among the most telling signatures is helium-3, a rare isotope produced in the mantle. Its presence, along with high concentrations of carbon dioxide, indicates that mantle-derived fluids are actively moving upward through fault zones. This is not a relic of ancient tectonics. It is a living system. When you stand here, Crossi remarked during a field survey, you're looking into a window that reaches all the way down to the mantle. Laboratory experiments and computer models provide further insight into how this process unfolds. In one experiment, Karlstrom used layers of colored ice to represent the crust and mantle. As the mountain block was eroded from above, the buoyant root beneath rose upward. When heat was introduced from below, the lower layers softened and began to spread apart. Cracks propagated from the surface downward, mirroring the way the Rio Grande Rift fractured the continent. This combination of isostatic rebound and thermal weakening explains why the Rockies did not simply collapse as erosion wore them down. Instead, they were rejuvenated from below. As their upper layers eroded, their deep roots bobbed upward, and hot mantle buoyed the thinned crust. Rather than a single mountain-building event frozen in time, the Rockies became a dynamic, evolving structure, rising, stretching, and cracking over tens of millions of years. The Rio Grande Rift remains geologically active today, though its motion is imperceptibly slow by human standards. A network of GPS stations anchored in bedrock along the length of the rift records relative motions of 0.5 to 2 millimeters per year. Over decades, this movement accumulates into measurable shifts, a silent but relentless unzipping of the continent. These modern instruments provide a level of precision unimaginable to early geologists. By comparing the positions of GPS stations through time, scientists can create detailed maps of deformation, track the widening of the rift, and even model how stresses are distributed in the crust. Yet perhaps the most remarkable implication of these studies is what they suggest about the future. If the current rate of extension continues for tens of millions of years, the Rio Grande Rift could eventually evolve into a full-fledged plate boundary, a new mid-continental rift system capable of splitting North America into two landmasses. Such a scenario is not unprecedented. The Atlantic Ocean itself began as a rift valley in Pangaea before widening into a vast ocean basin. The East African Rift today represents another stage in this process, where Africa is slowly dividing along a deep continental scar. The Rockies, then, are not simply relics of ancient compression. They are participants in a living tectonic drama that continues beneath our feet. In their roots and rifts, geologists read the story of a continent still in motion, stretched between the lingering memory of subduction and the rising heat of the mantle below. And as these forces reshape the land from below, they also give rise to something even more spectacular above ground: volcanoes. Part 6: Fire Beneath the Mountains. As the Rio Grande Rift slowly tore the crust apart, the weakened lithosphere became a conduit for heat and magma rising from the mantle. What had begun as subtle cracking soon evolved into something far more dramatic: volcanic activity. Across what is now New Mexico, Colorado, Utah, and Arizona, fire erupted through stone, reshaping the landscape in ways that are still visible today. The peak of this activity occurred between 37 and 25 million years ago, during the late Eocene and Oligocene epochs. During this time, a vast volcanic province known as the Southern Rocky Mountain Volcanic Field came to life. Over tens of millions of years, it produced thousands of eruptions, covering the region with thick layers of ash and lava. Among the most astonishing features of this province are the calderas, giant volcanic depressions formed when magma chambers emptied catastrophically during massive eruptions. The San Juan Mountains in southwestern Colorado hold some of the largest and best-preserved calderas on the continent. One of them, the La Garita caldera, erupted about 28 million years ago in what is considered one of the largest known explosive eruptions in Earth's history. The volume of material ejected is estimated at over 5,000 cubic kilometers, more than 50 times larger than the 1980 eruption of Mount St. Helens. Ash from La Garita blanketed large portions of North America, drifting as far east as Nebraska and Kansas. The eruption released so much material that the overlying ground collapsed, creating a depression more than 35 kilometers across. Today, this collapsed caldera forms a serene, forested basin, a quiet remnant of an almost inconceivable event. Geologists pieced together this story using a combination of field mapping, radiometric dating, and geophysical imaging. Volcanic tuffs, welded layers of ash and rock fragments, record the sequence of eruptions like tree rings. By analyzing minerals such as zircon within these tuffs, scientists can determine eruption ages with extraordinary precision, sometimes within tens of thousands of years. Meanwhile, seismic tomography, a technique that uses waves from earthquakes to image the Earth's interior, reveals low-velocity zones beneath the rift and volcanic fields, indicating areas of hot, partially molten mantle. These zones lie only tens of kilometers beneath the surface, much shallower than in surrounding regions, confirming that mantle heat remains unusually close to the crust beneath the southern Rockies. Chemical analyses of erupted rocks further support this picture. Basalts from the Rio Grande Rift contain mantle-derived isotopic signatures, such as elevated ratios of helium-3 and neodymium, indicating that their source lies deep within Earth's upper mantle rather than in recycled crustal material. These signatures match patterns observed in mid-ocean ridges and other active rift zones, reinforcing the idea that the rift is tapping into a deep and persistent source of heat. Importantly, this volcanic activity did more than just shape the landscape. It weakened the crust even further, amplifying the effects of extension. Every eruption that fractured the crust allowed more mantle heat to rise, in turn causing more thinning and more volcanism, a feedback loop that accelerated the evolution of the Rio Grande Rift. Even long after the most explosive eruptions ended, the region has remained geothermally active. Hot springs, fumaroles, and small cinder cones. The landscape from Colorado's San Luis Valley to central New Mexico. The Valles caldera, which last erupted about 1.25 million years ago, is a reminder that the system is far from dormant. Seismic swarms and ground deformation in the caldera continue to be monitored closely by the U.S. Geological Survey. Modern geophysical instruments have transformed how scientists understand these processes. GPS networks detect subtle ground movements as magma shifts underground. In SAR, interferometric synthetic aperture radar, satellites measure minute changes in ground elevation across entire volcanic fields. Seismometers capture the faint rumble of magma chambers inflating and deflating miles beneath the surface. Together, these data reveal a landscape that is still alive. The southern Rockies are not simply eroding relics of an ancient orogeny. They are perched above a mantle anomaly that continues to reshape the crust from below. This persistent heat has implications that extend far beyond geology. Volcanism and rifting interact with the atmosphere itself, injecting gases, altering climate, and influencing the composition of the air we breathe. During the peak of Oligocene volcanism, vast quantities of sulfur dioxide, carbon dioxide, and ash were lofted into the sky, affecting both local and global environments. To understand the full story of the Rockies, then one must look not only down into the Earth but also upward, into the thin, fragile layer of gases that envelopes the planet. That invisible shield has been shaped, in part, by the same geological forces that built mountains and tore continents apart. And in the modern era, new observations from space, including those focused on Pluto, are revealing just how exceptional Earth's atmospheric story truly is. Part 7: The Invisible Shield. Above the jagged peaks of the Rockies lies something far more fragile than granite: Earth's atmosphere. It is so thin that if the planet were the size of a basketball, the atmosphere would be no thicker than a coat of paint. Yet within this delicate film of gases resides everything that makes life on Earth possible: breathable oxygen, temperate climates, protection from deadly radiation, and a stable envelope that moderates extremes of heat and cold. Understanding how this invisible shield formed and how it has been maintained over billions of years requires us to look deep into Earth's geological heart. The atmosphere we breathe today is not primordial. It was built, destroyed, and rebuilt over immense spans of time by processes that are still active beneath our feet. The layers of the sky. Earth's atmosphere is divided into distinct layers. The troposphere, where almost all weather occurs, extends up to about 12 kilometers on average. The stratosphere, reaching up to 50 kilometers, contains the ozone layer that shields the surface from harmful ultraviolet radiation. The mesosphere, up to 85 kilometers, is where meteors burn. The thermosphere stretches hundreds of kilometers, hosting auroras and satellites. Beyond lies the exosphere, where the atmosphere thins into space. Despite this vertical stratification, the entire mass of the atmosphere is astonishingly light. 99% is contained within the first 30 kilometers above the surface. Gravity, temperature gradients, and the planet's magnetic field conspire to hold this gas envelope in place. A planet that breathes through stone. The earliest atmosphere, formed soon after Earth's accretion, was likely dominated by hydrogen and helium, light gases that quickly escaped into space. The atmosphere we have today is a secondary atmosphere, generated through outgassing from volcanoes, hydrothermal vents, and the mantle itself. Gases such as water vapor, carbon dioxide, sulfur dioxide, and nitrogen bubbled out of the young Earth's interior during relentless volcanic activity. As the planet cooled, water vapor condensed to form oceans, while carbon dioxide dissolved into seawater and was locked away in carbonate rocks. Nitrogen, chemically inert, accumulated steadily over time, eventually becoming the dominant atmospheric gas. Volcanism was, and remains, the planet's primary delivery system for atmospheric gases. Every eruption is a pulse of material from the deep Earth into the sky. Over billions of years, this process has built a stable atmosphere thick enough to support liquid water, a rarity in the solar system. The role of tectonics. Earth's atmosphere is not just the product of volcanism. It is regulated by plate tectonics. Subduction drags carbon-rich sediments into the mantle, where they are recycled and released again through volcanoes, a planetary-scale carbon cycle that acts as a long-term thermostat. When carbon dioxide levels rise, global temperatures increase, accelerating weathering of silicate rocks, which draws carbon back out of the atmosphere. When CO2 levels fall, weathering slows, allowing volcanic outgassing to build concentrations back up. This negative feedback loop has kept Earth's climate within a stable range for hundreds of millions of years, even as the sun's output has slowly increased. No other known planet has this dynamic. Mars, once volcanically active, lost its internal heat early. Without ongoing volcanism and plate tectonics, it could not replenish its atmosphere. Its magnetic field collapsed, and solar wind stripped away the thin gases that remained. Venus, by contrast, has no plate tectonics to sequester carbon. Its atmosphere became a runaway greenhouse, thick with carbon dioxide and sulfuric acid clouds. Earth alone sits between these extremes, its geology and atmosphere locked in a delicate and continuous dialogue, the shield against space. Another crucial component of atmospheric preservation is Earth's magnetic field. Generated by the churning of molten iron in the outer core, the geomagnetic field deflects charged particles from the solar wind. Without it, the atmosphere would be gradually eroded away, as happened on Mars. High above the Rockies, this magnetic shield is invisible but measurable. Satellites detect streams of energetic particles being diverted around the planet like water flowing around a stone. Auroras mark the places where some particles leak through, lighting up the sky in curtains of green and red. Volcanism, atmosphere, and life. Volcanism doesn't just shape the composition of the atmosphere, it interacts with it in real time. Major eruptions inject sulfur dioxide and ash into the stratosphere, where they reflect sunlight and temporarily cool the planet. Over longer timescales, carbon dioxide released by volcanoes can warm the climate, influencing glaciation cycles and sea levels. For example, The massive eruptions associated with the formation of the southern Rocky Mountain volcanic field likely had global climatic effects. Layers of ash found in marine sediments across North America record abrupt shifts in temperature and precipitation following major events like the La Garita eruption. This coupling of deep Earth processes and atmospheric dynamics underscores a central truth. Earth breathes through its mountains and volcanoes. The atmosphere is not separate from the planet. It is an extension of its geological activity. A delicate balance. The very forces that built the Rockies, subduction, uplift, volcanism, also helped craft and maintain the shield above them. Without continual outgassing, recycling, and magnetic protection, the air we depend on would have been lost long ago. And yet, this balance is not immutable. Geological, astronomical, or human-induced changes can tip it. By studying Earth's atmosphere in tandem with its interior dynamics, scientists have begun to understand how rare and fragile this equilibrium truly is. To grasp just how special Earth's atmospheric story is, however, we must look outward, to other worlds where this balance was never achieved or was lost. One such world lies at the frozen edge of our solar system, Pluto. Part 8. Pluto's Fading Breath. At the edge of our solar system, far beyond the orbits of Neptune, drifts a world so small and cold that for decades it was little more than a speck of light in our telescopes. Pluto, once the 9th planet, is now classified as a dwarf planet, but what it revealed during a single brief encounter in 2015 stunned planetary scientists. For decades, astronomers debated whether Pluto could even retain an atmosphere. At an average distance of nearly 6 billion kilometers from the Sun, temperatures on its surface plunge below -220 degrees Celsius. At such extremes, most gases should freeze solid. And yet, observations from Earth-based telescopes in the late 20th century detected a faint haze around Pluto during stellar occultations, suggesting it possessed a tenuous but real atmosphere, a thin veil of volatile ices. Pluto's atmosphere is primarily composed of nitrogen, with traces of methane and carbon monoxide. These gases originate from the sublimation of surface ices when Pluto approaches perihelion, the closest point in its elliptical orbit around the Sun. As sunlight warms the surface, the ices vaporize, forming a thin atmosphere that envelopes the planet. But unlike Earth, Pluto lacks both a strong gravitational field and a magnetic shield. Its atmosphere is ephemeral, expanding and contracting dramatically over the course of its 248-year orbit. As it moves toward aphelion, the farthest point from the Sun, temperatures drop and the atmosphere freezes back onto the surface, collapsing into a layer of frost. The New Horizons revelation. When NASA's New Horizons spacecraft flew past Pluto on July 14, 2015, it provided humanity's first direct look at this distant world. As it passed behind Pluto relative to the Sun, the spacecraft's instruments observed the occultation of sunlight, allowing scientists to measure the structure of Pluto's atmosphere with unprecedented precision. The data revealed something astonishing. A layered haze stretching up to 150 kilometers above the surface, far higher than anyone had anticipated. These layers were composed of tiny particles formed when ultraviolet light from the distant Sun broke apart methane molecules, triggering complex chemical reactions that produced hydrocarbons and tholins, organic compounds that give Pluto its reddish hue. New Horizons also detected a significant rate of atmospheric escape. Pluto's weak gravity allows nitrogen and methane molecules to leak into space at a rate of roughly 500 tons per hour during peak atmospheric activity. This outflow is driven by solar radiation and by the fact that Pluto's escape velocity is only about 1.2 kilometers per second, far lower than Earth's 11.2 kilometers per second. In effect, Pluto is constantly exhaling into space, and its atmosphere is being stripped away molecule by molecule. Planet without protection. Pluto has no global magnetic field to shield it from the solar wind. Instead, the solar wind interacts directly with its upper atmosphere, creating a comet-like tail of escaping particles that stretches millions of kilometers downstream. Measurements from New Horizons SWAP instrument, solar wind around Pluto, showed that the solar wind slows and diverts around Pluto, forming a shock similar to a weak bow wave. But unlike Earth, Where the magnetosphere protects the lower atmosphere, Pluto's thin veil is vulnerable. Over millions of years, these interactions contribute to the gradual erosion of its gases, thinning its atmosphere with each orbit. Seasonal breathing on a planetary scale. Pluto's orbit is highly elliptical and tilted, leading to extreme seasonal variations. When it is closest to the Sun, its atmosphere swells dramatically as surface ices sublimate. Some models predict that during perihelion, surface pressures can reach 10 microbars, still less than 100,000th of Earth's atmospheric pressure at sea level, but significant for a world this small. As it moves outward toward aphelion, these gases recondense onto the surface. Over the coming decades, Pluto is expected to grow colder and its atmosphere to collapse almost entirely, leaving only a thin layer of frost. This cyclical appearance and disappearance of an atmosphere is unlike anything on Earth. Here, tectonics and a magnetic shield sustain a relatively stable envelope. On Pluto, the atmosphere is temporary, tied directly to sunlight and surface temperature rather than internal geological recycling. Atmospheric escape, a universal process. The fate of Pluto's atmosphere highlights the universal physics governing all planetary atmospheres. Escape velocity, solar radiation, magnetic shielding, and geological activity. Worlds with insufficient gravity or protection are constantly bleeding gases into space. Mars, too, suffered this fate. Once home to rivers and a thicker atmosphere, it lost its magnetic field and was stripped by the solar wind. Pluto represents this process in an even more extreme environment, where solar energy is weak but gravitational retention is weaker still. In contrast, Earth's combination of gravity, tectonic outgassing, magnetic protection, and feedback cycles has allowed it to maintain a thick atmosphere over billions of years. The cosmic context. By studying Pluto's vanishing breath, scientists gain a mirror against which to measure Earth's exceptional stability. The data from New Horizons forced researchers to refine models of atmospheric escape, not just for Pluto, but for exoplanets orbiting distant stars. Many small, rocky worlds may have once had atmospheres but lost them quickly through escape processes similar to Pluto's. Pluto, in this sense, is both a relic and a warning. Its atmosphere tells a story of fragility, of how thin the line is between a living sky and a frozen silence. And this story is not confined to distant space. The same forces that erode Pluto's atmosphere exist in our solar system and beyond. What protects Earth is not permanence, but a set of fortunate and dynamic geological conditions. If those conditions change, even a robust atmosphere can falter. As Earth's magnetic field drifts, tectonic plates shift, and human activity alters atmospheric composition, Pluto's fading haze reminds us of what can happen when planetary systems lose their balance. Part 9 echoes across worlds. The revelations from Pluto did more than deepen our understanding of a distant dwarf planet. They cast a long shadow back toward Earth, forcing scientists, policymakers, and the public to reconsider what it truly means for a planet to hold on to its sky. In 2015, as New Horizons sped through Pluto's faint atmosphere and returned its breathtaking data, a cascade of international collaborations ignited. Observatories across Europe, Asia, and South America synchronized their telescopes to watch stellar occultations, recording how starlight dimmed and refracted as Pluto passed in front. These measurements, paired with the spacecraft's close-range observations, created the most detailed atmospheric profile ever obtained for any world beyond Mars. At the same time, Earth itself was being scrutinized from afar. Satellites from NASA, ESA, and JAXA were continuously monitoring Earth's ionosphere, magnetosphere, and upper atmosphere, particularly during periods of heightened solar activity. The mid-2010s saw several intense solar storms, including a powerful coronal mass ejection in March 2015 that triggered brilliant auroras visible as far south as Colorado and Germany. These solar events served as a living laboratory. Instruments measured how charged particles interacted with Earth's magnetic shield and upper atmosphere. The contrast with Pluto was stark. Where Earth deflected the storm like a ship cutting through waves, Pluto absorbed the solar wind like a drifting iceberg, losing part of its atmospheric skin in the process. historical parallels and shifting perspectives. This comparison between Earth and Pluto echoed earlier scientific revolutions. In the late 19th and early 20th centuries, the discovery that mountains like the Rockies were once undersea floors overturned centuries of static views of the Earth. In the late 20th century, the plate tectonic revolution reframed our understanding of continents and oceans. And now, in the early 21st century, planetary atmospheric science was undergoing a similar transformation. For much of human history, the atmosphere was viewed as permanent and passive, an unchanging backdrop to human affairs. Pluto's seasonal, fragile haze and Mars's stripped sky forced scientists to think in planetary timescales, where atmospheres are active participants in geological and cosmic dramas. The geopolitics of the sky. These discoveries didn't remain confined to laboratories and observatories. Atmospheric stability and space weather became strategic issues. Nations reliant on satellite infrastructure realized that solar storms, the same forces that erode Pluto's atmosphere, could cripple communications, navigation, and power grids. International organizations like the World Meteorological Organization, WMO, and the International Space Environment Service began coordinating space weather forecasts with the same urgency once reserved for hurricanes and earthquakes. The European Space Agency launched missions like Solar Orbiter, while NASA expanded its heliophysics program to better understand the Sun's interaction with planetary atmospheres. In parallel, debates over Earth's changing climate gained renewed intensity. The geological perspective that atmospheres can be built and lost sharpened the urgency of human-driven changes. If natural forces can strip a planet's sky over millennia, what might unchecked industrial activity achieve in mere centuries? A broader scientific conversation. Within the scientific community, Pluto's atmosphere became a test case for refining models of atmospheric loss and evolution. Researchers used data from New Horizons to adjust escape rate equations, comparing them with Earth, Mars, and exoplanet observations. These refinements had unexpected consequences. They changed how astronomers interpreted signals from distant worlds. For years, the presence of certain gases in exoplanet atmospheres, such as oxygen or methane, had been considered potential biosignatures. But Pluto showed that non-biological processes could create, layer, and dissipate gases in complex ways. The thin haze around Pluto is not life-made, but it mimics some atmospheric signals that telescopes might detect on faraway planets. This realization influenced how upcoming missions, such as the James Webb Space Telescope and ESA's Ariel, plan to analyze exoplanetary atmospheres. Pluto, a tiny world at the solar system's edge, had altered the strategy for searching for life across the galaxy. Cultural ripples. Beyond science and politics, these discoveries resonated culturally. Documentaries and podcasts drew poetic parallels between Pluto's vanishing breath and Earth's fragile blue shell. Artists depicted Pluto's haze trailing off into the solar wind like a ghost, while environmental movements used these images to underscore the impermanence of planetary atmospheres. In classrooms, students compared escape velocities and atmospheric compositions, calculating why Pluto loses its air while Earth keeps hers. The exercise wasn't just academic. It was existential. It showed, in stark terms, how narrow the conditions are for a stable, breathable world. An interconnected system. Perhaps the most profound insight to emerge was a sense of planetary interconnectedness. Earth, Mars, Pluto, and distant exoplanets all obey the same physical laws. What differs are the initial conditions and the evolving balances between gravity, magnetic fields, solar energy, and geological activity. The Rockies' rise, the persistence of Earth's atmosphere, and Pluto's fading haze are not separate stories. They are chapters in the same planetary narrative, governed by tectonics, cosmic radiation, and time. As astronomers refine their models and geologists read the mountains like pages of an ancient book, a sobering thought emerges. Earth's atmosphere is not a permanent gift. It is a maintained state, and maintenance requires energy from the core, from tectonics, from the magnetic shield. Without them, even worlds rich in air can fall silent. In the decades after New Horizons, new missions would extend this comparative study, probing even further into the edges of the solar system. But the central question remained the same. Why do some worlds keep their skies while others let them go? Part 10: Skies That Come and Go. Long before spacecraft revealed Pluto's haze and satellites mapped the upper reaches of Earth's sky, the heavens had already been shaping the atmosphere in ways both subtle and catastrophic. The sky is not merely a container of gases. It is an active participant in the solar system's ongoing drama, continuously bombarded, altered, and occasionally rewritten by cosmic events. The celestial showers. Every year, the Earth passes through trails of dust and debris left behind by comets. These streams produce meteor showers like the Perseids and Leonids, dazzling displays that streak across the night sky. But beyond their beauty lies a quiet, persistent influence: the daily delivery of extraterrestrial material. Estimates suggest that between 5 and 300 tons of cosmic dust enter Earth's atmosphere each day. Most of it burns up in the mesosphere, creating faint trails of ionized gas that reflect radar. Over geologic timescales, this influx subtly alters atmospheric chemistry, seeding the upper atmosphere with metals like iron and sodium. These particles play roles in noctilucent clouds, polar mesospheric layers, and even in the formation of condensation nuclei for high-altitude ice. On Pluto, by contrast, the influx of interplanetary dust is minuscule. Its tenuous atmosphere and weak gravity mean that most cosmic particles sail past unimpeded. Earth's thicker atmosphere not only burns these particles, but incorporates them into its cycles. A small but meaningful distinction that reinforces how our planet's atmosphere participates in the solar system's material exchange. When rocks fall from the sky, not all visitors from space are dust. Throughout its history, Earth's atmosphere has been repeatedly tested, and sometimes transformed by large impacts. Around 66 million years ago, a 10-kilometer-wide asteroid struck near what is now Chicxulub, Mexico, releasing energy equivalent to billions of Hiroshima bombs. The impact blasted dust, sulfur, and vaporized rock high into the stratosphere, triggering global darkness and a collapse of photosynthesis. This event marked the Cretaceous-Paleogene (KPG) extinction, wiping out 75% of species, including most dinosaurs. But from an atmospheric perspective, it also served as a profound stress test. The stratospheric aerosols produced by the impact persisted for months to years, cooling the planet dramatically before slowly settling out. Earth's atmosphere recovered because it had buffers: active volcanism to replenish gases, oceans to absorb and redistribute heat, and tectonics to regulate long-term carbon cycles. A thinner, weaker atmosphere, like that of Mars or Pluto, might not have survived such a shock. Ancient rhythms and climatic swings. Beyond sudden impacts, Earth's atmosphere has responded to cyclical astronomical forces. Milankovitch cycles, periodic variations in Earth's orbit and axial tilt, drive long-term climate oscillations, including the waxing and waning of ice ages. These cycles, with periods ranging from tens to hundreds of thousands of years, modulate the amount of solar energy Earth receives, particularly at high latitudes. The atmosphere amplifies these changes through feedback loops. For example, when orbital configurations cool the poles, ice sheets grow, reflecting more sunlight and cooling the planet further. Atmospheric carbon dioxide drops as colder oceans absorb more, deepening the chill. Conversely, warmer orbital phases trigger CO2 release, amplifying warming. Pluto experiences its own extreme orbital cycles, but with a crucial difference. Lacking tectonic recycling and a dense atmosphere, it cannot stabilize these swings. Instead, its entire atmosphere appears and vanishes in response, freezing onto the surface when solar energy wanes. Earth's dynamic geology transforms similar orbital nudges into gradual climate shifts rather than wholesale atmospheric collapse. The atmosphere as an archive. Ice cores drilled from Antarctica and Greenland contain trapped bubbles of ancient air, offering a window into past atmospheres stretching back hundreds of thousands of years. They reveal rhythmic rises and falls in CO2, methane, and temperature, a heartbeat regulated by orbital cycles and buffered by tectonic and biological feedbacks. Beyond ice, Sedimentary rocks record atmospheric shifts across millions of years. Layers of ash, silt, and chemical precipitates reveal times when volcanic events spiked greenhouse gases, when meteors darkened skies, or when oxygen surged during the Great Oxidation Event. Pluto lacks such archives. Its atmosphere and surface reset with each seasonal cycle, erasing long-term records like sand swept clean by the wind. Earth's thick, sustained atmosphere, combined with active geology, allows it to remember its own history, and that memory is what enables scientists to predict its future. Potential futures and warnings. When scientists place Earth and Pluto side by side, one question emerges. What happens if Earth's geological engines slow down? If tectonic activity wanes, volcanic outgassing would diminish. The carbon cycle would stall. Over millions of years, CO2 would be drawn down by weathering and locked into rocks, potentially thinning the atmosphere. Without magnetic protection, the solar wind would gradually strip gases from the upper layers. The sky might not vanish overnight, but over tens of millions of years, Earth could grow colder, drier, and thinner skied, more like Mars than its current self. Conversely, if greenhouse gases rise too quickly, through massive volcanic events or human activity, feedback loops could push the atmosphere toward runaway states resembling ancient Venus, where surface temperatures soared and water was lost irreversibly to space. The atmosphere, then, is both resilient and fragile. It can absorb cosmic shocks and climatic swings, but only as long as the deep Earth continues to power its renewal and regulation. The cosmic perspective. Viewed from space, Earth's atmosphere is a thin, glowing line against the blackness, a fragile boundary separating life from the void. Pluto's haze, by contrast, is a faint blue halo that appears briefly and then fades into darkness. These two worlds exist along a spectrum defined by energy, gravity, time, and chance. Meteor showers, orbital cycles, tectonic breathing, solar storms, volcanic outbursts, all are threads in the same tapestry. Together, they tell a story of skies that come and go, of atmospheres as temporary states maintained by delicate balances rather than immutable walls. In this broader context, the Rocky Mountains are not just remnants of ancient collisions. They are part of the planetary machinery that keeps Earth's atmosphere alive, rising, eroding, and feeding the cycles that regulate our air. And Pluto, drifting silently at the edge of the sun's influence, is a reminder of what happens when those machines fall silent. Part 11, Futures Written in the Air. As our instruments gaze farther into space and deeper into time, one realization becomes increasingly clear. Atmospheres are temporary stories written in gas. They begin, change, and end according to the shifting balance between geology, solar energy, and chance. Earth's sky, for all its resilience, is no exception. The future of our atmosphere will be shaped by both natural processes and human choices, each operating on different but intersecting timescales. Natural trajectories. If we project Earth's geological and astronomical trends forward tens of millions of years, the atmosphere's fate can be outlined in broad strokes. Plate tectonics, driven by the planet's internal heat, is gradually slowing as Earth cools. In hundreds of millions of years, subduction may cease altogether. Without it, volcanic outgassing would decline, weakening the carbon cycle that stabilizes climate. Carbon dioxide would be drawn down by weathering and stored in rocks, thinning the atmosphere and cooling the surface. Simultaneously, the sun's luminosity is slowly increasing by roughly 10% every billion years. Within a few hundred million years, this increase will warm Earth enough to accelerate ocean evaporation. Water vapor, a powerful greenhouse gas, will amplify heating until a tipping point is reached. Eventually, the oceans could boil away, and hydrogen escaping into space would leave behind a hot, arid planet, not unlike ancient Venus. These scenarios unfold on immense timescales, but they mirror processes already observed on other worlds. Mars losing its atmosphere through lack of internal activity, Pluto freezing and sublimating in rhythmic cycles, Venus tipping into runaway greenhouse conditions. Anthropogenic acceleration. Against these slow natural arcs stands the unprecedented pace of human-induced atmospheric change. In just 2 centuries, industrial civilization has released vast amounts of carbon dioxide, methane, and other greenhouse gases, pushing atmospheric composition beyond anything seen in at least 3 million years. Ice core records, marine sediments, and fossilized pollen reveal that previous CO2 fluctuations occurred over thousands of years. Today, equivalent shifts happen in mere decades. Climate models, grounded in physics and confirmed by observation, show rising global temperatures, melting ice sheets, changing weather patterns, and ocean acidification. The geological thermostat that has buffered Earth's atmosphere for eons was not designed to handle such rapid forcing. Feedback mechanisms that typically operate over tens of thousands of years are being overwhelmed on a human timescale. Some scientists argue that we are entering a new atmospheric epoch, comparable in significance to the Great Oxidation Event 2 billion years ago, but this time driven not by microbes, but by technology and industry. Space-based observations and the global view. From orbit, Earth's atmosphere is monitored with an intensity once reserved for distant planets. Satellites like NASA's Terra, ESA's Sentinel series, and Japan's GOSAT track greenhouse gases, aerosols, and temperature changes across the globe. Instruments detect subtle shifts in the ionosphere caused by solar storms, stratospheric chemistry altered by human emissions, and tropospheric patterns of pollution and cloud cover. These data are not merely scientific. They have become geopolitical tools. Nations rely on them to verify emissions, forecast climate impacts, and coordinate responses to extreme weather. The atmosphere has become both a shared resource and a shared vulnerability, much like the oceans. International reactions and policy. The fragile, interconnected nature of atmospheres, illuminated by studies of Pluto, Mars, and Earth, has prompted unprecedented international discussions. Agreements like the Paris Accord and global frameworks for space weather monitoring are early attempts to manage atmospheric stability on a planetary scale. Space agencies collaborate to observe solar activity and atmospheric escape, recognizing that a powerful coronal mass ejection could disrupt satellites, power grids, and communications worldwide. The same solar forces that strip Pluto's atmosphere can, on Earth, trigger cascading technological failures. Scientific debates and emerging hypotheses. Amid this growing attention, scientific debates have intensified. Some researchers propose geoengineering approaches, deliberate interventions to stabilize the atmosphere, such as injecting reflective aerosols into the stratosphere or capturing CO2 at planetary scales. Proponents argue that these may be necessary stopgaps. Critics warn of unpredictable side effects and ethical hazards. Others question whether tectonic slowing will indeed lead to atmospheric decline, pointing to potential feedbacks from mantle plumes or unforeseen biological adaptations. A few radical hypotheses suggest that future human civilizations could artificially sustain tectonic-like cycles, using massive geo-industrial infrastructure to regulate atmospheric composition in lieu of natural processes. And at the speculative edge, planetary scientists look to Pluto and exoplanets to test fundamental theories of atmospheric stability. Could small, icy worlds sustain temporary atmospheres through engineered means? Could Earth's atmosphere, if destabilized, be artificially maintained over geologic timescales? These are not merely thought experiments. They are being modeled with increasing seriousness as humanity contemplates its long-term survival. Echoes of other worlds. The comparative study of atmospheres has transformed how scientists think about Earth's future. Pluto's vanishing haze, Mars's lost rivers, and Venus's runaway heat are no longer distant curiosities. They are possible futures, reminders that atmospheric states are conditional. In this light, the Rockies stand as silent witnesses to Earth's deep time story. Their uplift fueled volcanic outgassing that helped sustain the atmosphere. Their erosion feeds chemical weathering that draws carbon from the sky. If these geological engines falter, the atmosphere's balance will shift. And if human activities accelerate that shift too far, the stable sky we inherit may not be the one we leave behind. Part 12. The Signal in the Sky. In early 2032, as solar activity surged toward the peak of solar cycle 26, a quiet anomaly appeared in Earth's upper atmosphere. It began as a faint blip in data transmitted from a constellation of ionospheric monitoring satellites, part of a joint European-Japanese program designed to track space weather impacts on global communication systems. The anomaly was subtle at first, a narrowband oscillation detected in the thermosphere, approximately 120 kilometers above the Rocky Mountains. At that altitude, the air is thinner than the best laboratory vacuum, and temperature fluctuations are normally driven by solar flux and geomagnetic storms. But this signal did not match any known solar or geomagnetic pattern. It had a periodicity of 47 minutes, persisted for several days, and appeared to propagate laterally across thousands of kilometers without dispersing. No solar flares were recorded during the interval. No atmospheric gravity wave models predicted a pattern of this frequency. It was, in the words of one mission scientist, a fingerprint we've never seen before. Detection. The signal was first noticed by Takuya Ishikawa, a data analyst at JAXA's Space Weather Division. Tasked with routine quality checks, he spotted an odd rhythmic pattern in magnetometer readings and flagged it for further review. Within 48 hours, teams from ESA, NASA, and Canada's Atmospheric Research Network had confirmed the anomaly across multiple instruments: magnetometers, accelerometers, and GPS occultation sensors. The geographic epicenter of the signal traced a rough oval centered over northern Colorado and southern Wyoming, exactly above the region where the Rio Grande Rift terminates and where ancient thrust faults of the Rockies intersect. Initial hypotheses. Early explanations ranged widely. Some suggested the oscillation could be a new form of atmospheric gravity wave triggered by unusual jet stream patterns. Others speculated that it was related to the intensifying solar wind. A few proposed more exotic ideas: resonance between the atmosphere and crustal structures, electromagnetic coupling driven by the underlying geology, or even subtle interactions between the mantle plume beneath the region and the ionosphere. What made the phenomenon particularly striking was its coherence. Typically, atmospheric oscillations at those altitudes dissipate rapidly. This one persisted with mathematical precision, like a tuning fork vibrating in the upper sky. Escalation. Within weeks, research groups mobilized. The U.S. Geological Survey dispatched seismic arrays and magnetotelluric instruments to Colorado and New Mexico to measure ground-based signals that might correlate with the atmospheric data. High-altitude balloons were launched from White Sands in Alberta, equipped with sensors to probe temperature gradients, plasma densities, and electromagnetic fluctuations. Meanwhile, ESA redirected one of its low Earth orbit satellites to conduct repeated occultation passes through the affected region. The results were baffling. The signal intensified at night, when solar forcing was weakest. Instead of fading as expected, it amplified, suggesting an internal energy source rather than an external one. Historical context. Archival data revealed that similar oscillations had been faintly recorded but ignored during two previous periods, 1998 and 2015, both during peaks in solar activity. In those cases, the signal was dismissed as instrumentation noise. Now, with more sensitive arrays, its structure became undeniable. The recurrence every solar maximum hinted at a cyclical trigger, perhaps a resonance effect between geomagnetic conditions and deep Earth processes. Several geophysicists pointed out that the anomaly's epicenter lay above one of the thinnest segments of continental crust in North America, where the Rio Grande Rift and the ancient thrust belts intersect over anomalously hot mantle. This region had long been a geological crossroads, where forces of compression and extension overlapped. Could the signal be evidence of some previously unknown coupling between Earth's interior and its upper atmosphere? Public attention. When amateur radio operators in the American Midwest began detecting unusual VLF, very low frequency, disturbances that mirrored the oscillation's timing, the story broke into the public domain. Newspapers dubbed it the Sky Pulse. Social media buzzed with speculation ranging from secret military tests to alien communication. Scientists, caught between intrigue and skepticism, convened an emergency session at the American Geophysical Union. the consensus was cautious. The sky pulse was real, reproducible, and unexplained, and it was strongest above the Rockies, the very mountains whose rise had once rewritten North America's landscape. Toward a breakthrough. In late August 2032, as data poured in, a team at the European Space Operations Center, ESOC, noticed something extraordinary. When the sky pulse's intensity was mapped against Pluto's orbital position, a faint but statistically significant correlation emerged. The oscillation tended to appear when Pluto was near heliocentric longitudes associated with its perihelion arc. First, this seemed absurd. How could a dwarf planet billions of kilometers away influence oscillations in Earth's upper atmosphere? Most dismissed it as coincidence. But a small group of atmospheric physicists and orbital dynamicists began to wonder if Pluto's position was acting as a proxy for some larger cyclical solar phenomenon, perhaps tied to the outer solar system's gravitational resonances and their effect on solar magnetic field dynamics. Whatever the cause, one thing was clear. This was not just another atmospheric curiosity. Something deep, cyclical, and poorly understood was manifesting high above the Rockies. And it was only the beginning. Part 13, The Deep Connection. By late 2032, the sky pulse was no longer an isolated curiosity confined to atmospheric specialists. It had become a global scientific priority. Research teams across continents were pulled into an unprecedented interdisciplinary investigation that spanned seismology, atmospheric physics, solar science, and planetary dynamics. The more data they gathered, the stranger the picture became. Global coordination. The United Nations Committee on the Peaceful Uses of Outer Space (COPUOS) convened an emergency working group to coordinate satellite resources. Within weeks, a patchwork network emerged. NASA's Gold and Icon missions provided thermospheric imaging. ESA repositioned swarm satellites to measure magnetic field perturbations. JAXA contributed high-resolution ionospheric spectrometers. Canada deployed its ground-based SuperDARN radar arrays to sweep the upper atmosphere above the Rockies in real time. For the first time, instruments designed for space weather monitoring were pointed not outward toward the sun, but downward, toward a persistent oscillation over North America. Anomalies underground. While satellite teams tracked the oscillation above, geophysicists turned their gaze below. Seismic stations across Colorado, New Mexico, and Wyoming were cross-correlated with atmospheric pulse timings. What they found sent ripples through the scientific community. Roughly 6 minutes before each atmospheric pulse intensified, a cluster of deep, low-frequency seismic tremors registered beneath the southern Rockies. These tremors originated at depths of 45 to 60 kilometers, far deeper than typical crustal earthquakes and well within the upper mantle. They were too faint to be felt on the surface, but their periodicity matched the 47-minute atmospheric signal with astonishing precision. The leading hypothesis quickly shifted. The sky pulse wasn't purely atmospheric. It appeared to be a coupled phenomenon, linking the deep mantle to the upper thermosphere through some as-yet unidentified pathway. Mantle-ionosphere coupling. This idea was not entirely new. In the early 21st century, a handful of studies had speculated that electromagnetic and acoustic gravity waves could connect deep Earth processes to the ionosphere. Large earthquakes sometimes produced traveling ionospheric disturbances, TIDs. Volcanic eruptions could send pressure waves into the upper atmosphere. But nothing on record matched the regularity or intensity of the sky pulse. One proposed mechanism involved electromagnetic induction. If mantle material beneath the Rockies contained significant conductive minerals, cyclical pressure changes could generate EM fields that propagated upward through the crust. Another hypothesis pointed to fluid movement in the mantle wedge, driving oscillatory stress that radiated upward as gravity waves. Neither fully explained the observed coherence. But both hinted at a hidden resonance, a natural frequency of the Earth-atmosphere system that had gone unnoticed until technology became sensitive enough to detect it. The leak. In November 2032, the investigation took an unexpected turn when a confidential technical report from the European Space Operations Center, ESOC, was leaked to a consortium of science journalists. The report summarized months of analysis on the Pluto correlation. Contrary to public statements that the correlation was statistically marginal, the leaked document revealed that during 3 historical Skypulse episodes, 1998, 2015, 2032, Pluto was positioned within a narrow heliocentric longitudinal window associated with a periodic modulation of the solar magnetic field. According to the report, researchers at ESOC and the Max Planck Institute for Solar System Research had developed a working model. The outer planets subtly modulate solar magnetic field harmonics through gravitational magnetic interactions. These harmonics, in turn, influence Earth's magnetosphere in ways that, under specific geological conditions, can trigger resonance between the mantle and thermosphere. The model was incomplete, more a framework than a proof, but its implications were staggering. It suggested that the Skypulse might be the surface manifestation of a solar system-scale rhythm, mediated through deep Earth structures. Scientific and political shockwaves. The leak detonated across media channels. Headlines proclaimed, "Dwarf planet linked to Earth's sky mystery," and "Deep Earth hums to a cosmic beat." Politicians demanded briefings. Some accused space agencies of withholding information. Conspiracy theories flourished online, ranging from claims of alien transmitters to secret geological weapons. Amid the chaos, the scientific community scrambled to stay ahead of misinformation. At a hastily convened conference in Geneva, atmospheric physicists, geophysicists, and solar scientists presented preliminary findings. Though cautious, they agreed on 3 points. The Skypulse was real and reproducible. It was likely caused by a coupled Earth-space phenomenon involving both internal and external drivers. Understanding it required a level of interdisciplinary cooperation never before attempted. The breakthrough data. Late that December, the breakthrough came from an unexpected source. A small university CubeSat launched by a consortium of Canadian and German students. Orbiting in low Earth orbit, it carried a magnetometer and plasma analyzer of surprisingly high sensitivity. As it passed over the Rockies during a particularly intense Skypulse episode, it recorded a precise phase shift between the atmospheric oscillation and a deep electromagnetic anomaly rising from below. The data showed a vertical standing wave, energy oscillating between the upper mantle and thermosphere like a string plucked between 2 fixed points. The implication was stunning. Earth's interior and its upper atmosphere were resonating in a synchronized loop, excited by subtle modulations in the solar magnetic field. For the first time, the Skypulse had a plausible physical mechanism, one that tied together mountains, mantle, atmosphere, and distant planetary orbits into a single extraordinary system. But the discovery raised a new and unsettling question. Had this resonance always been there, quietly humming through deep time, or was it growing stronger? Part 14. The resonance grows. In the early weeks of 2033, just as most research teams were preparing to settle into a long, methodical study of the Skypulse, the phenomenon changed. The oscillations, once confined to a narrow oval above the southern Rockies, intensified by nearly 40% in amplitude over a span of only 2 weeks. More startlingly, monitoring stations in Scandinavia, the South Pacific, and Central Asia began reporting weaker but phase-locked echoes of the same 47-minute signal. What had been a regional anomaly was becoming a planetary phenomenon. Satellite disturbances. The first practical signs appeared not in scientific journals but in satellite control rooms. Operators of the European Galileo navigation system noticed irregular timing drifts between some of their spacecraft. Similar glitches were reported by the US GPS constellation and Japan's QZSS system. At first, engineers suspected software faults or solar storms. But solar activity remained moderate, and system diagnostics returned clean. A deeper look revealed that the ionospheric corrections used to maintain precise positioning were being periodically skewed, exactly in rhythm with the Skypulse. Low Earth orbit satellites experienced anomalous drag variations, as if the upper atmosphere were subtly breathing in synchrony with the pulse. The variations were small, mere millimeters per second, but enough to throw off delicate orbital predictions. By February, at least 3 Earth observation satellites had to execute unexpected thruster burns to maintain formation. Mission planners were alarmed. A persistent, global, resonant oscillation in the upper atmosphere was not something any agency had planned for. Scientific escalation. The scientific community, already stretched thin, shifted into emergency collaboration. Working groups met around the clock across time zones, trading terabytes of seismic, magnetic, and atmospheric data in real time. The sky pulse, once dismissed as a curiosity, now demanded the attention of geophysicists, plasma physicists, orbital dynamicists, and climatologists simultaneously. At NASA's Goddard Space Flight Center, an interdisciplinary team overlaid 40 years of geomagnetic, seismic, and solar data. They found faint signatures of the sky pulse in historical magnetometer archives stretching back to at least 1972, but it had grown progressively stronger over the decades, paralleling rising solar activity cycles and possibly even shifts in Earth's rotation parameters. Meanwhile, deep seismic sensors in Colorado and New Mexico detected an uptick in the low-frequency tremor clusters that preceded each atmospheric oscillation. Their frequency increased from 1 every 47 minutes to 2 nested harmonics at 47 and 23.5 minutes, indicating that the resonance was splitting into multiple modes, a hallmark of a system entering a new dynamical regime. International tensions. As the phenomenon escalated, political tensions rose. Satellite glitches affected navigation, agriculture, shipping, and financial systems dependent on precise timing. Some governments quietly blamed others for potential covert technologies. Conspiracy narratives spread faster than official explanations. At the United Nations, a special session was convened to address the sky pulse disruptions. Delegates from multiple nations demanded transparency from space agencies. Others called for a moratorium on certain classified satellite operations, suspecting military interference. The scientific representatives could only repeat what they knew. The sky pulse was real. It was growing. Its cause involved deep Earth structures and solar magnetic harmonics. No nation had the capability to generate or control such a phenomenon. Unexpected climate signals. Amid the technological disruptions, atmospheric scientists noticed something else. Temperature and pressure anomalies in the thermosphere and upper stratosphere began to oscillate in sync with the sky pulse. Though small changes of a few degrees Kelvin, these oscillations were globally coherent. Preliminary models suggested that if the resonance continued to amplify, it could alter the propagation of planetary waves, potentially affecting jet streams and weather patterns. What had started as an obscure atmospheric vibration was now brushing against the planet's climate engine. Pluto's position and solar dynamics. At ESA's Solar Observatory in La Palma, researchers refined the Pluto solar magnetic model. They found that Pluto was nearing the same longitudinal alignment it occupied during the 1998 and 2015 Skypulse episodes, but now the Sun's magnetic field was in an unusually strong, twisted configuration, a result of consecutive intense solar cycles. In this configuration, subtle gravitational perturbations from the outer planets seemed to modulate solar magnetic flux in a rhythmic way, like fingers plucking a taut string. Earth, with its conductive mantle wedge beneath the Rockies, appeared to be uniquely tuned to resonate with this pattern. Planet-sized instrument. One of the more poetic but accurate descriptions came from geophysicist Dr. Marissa Koenig during a Geneva briefing. It's as if the Earth is an instrument, and for the first time, something out there has found its resonance frequency and struck the note. No one yet understood whether this note represented a temporary harmonic, like a bell ringing after a strike, or a sustained oscillation that could build toward unpredictable consequences. Public reaction. The story broke worldwide when leaked satellite telemetry revealed the scale of orbital corrections being made. News outlets ran dramatic graphics showing pulsing rings around Earth. Documentaries called it the planet's hidden heartbeat. Public fascination mixed with anxiety. Some viewed it as evidence of a grand cosmic harmony. Others feared it was a precursor to disaster, a seismic superevent or geomagnetic collapse. Religious groups, conspiracy forums, and scientific podcasts all seized the narrative in different ways. Through it all, the data kept streaming in and the sky pulse grew louder. The question hanging over every research lab, control room, and diplomatic chamber was no longer whether the phenomenon was real, but What happens if it keeps amplifying? And beneath the Rockies, the birthplace of the signal, deep tremors hinted that the answer might lie not in the sky, but in the Earth's interior itself. Part 15: The Heart of the Pulse. By mid-2033, the sky pulse had become the single most closely monitored natural phenomenon on Earth. Satellites, seismic arrays, magnetometers, atmospheric probes, and supercomputers were all enlisted in the effort to understand, or at least anticipate, what was unfolding. What began as a faint, localized oscillation had grown into a planet-wide resonance, subtly altering the upper atmosphere and beginning to affect the infrastructure of modern civilization. Amid the escalating urgency, three developments converged to provide the decisive breakthrough: a deep Earth seismic anomaly, a high-altitude plasma wave detection, and an unprecedented solar magnetic event. 1. The mantle anomaly. Deep beneath the southern Rockies, at a depth of nearly 1,200 kilometers, far below the upper mantle tremor sources, a seismic tomography array operated by the U.S. Geological Survey and the German Research Center for Geosciences imaged an anomaly unlike any previously recorded. It appeared as a column of unusually conductive mantle material, stretching vertically through the lower mantle and connecting to the base of the upper mantle beneath the Rio Grande Rift. Seismic velocities slowed dramatically in this column, and magnetotelluric measurements suggested that molten or partially molten rock rich in conductive minerals was oscillating in synchrony with the sky pulse. The column acted like a gigantic resonant cavity, channeling energy between the planet's deep interior and its upper atmosphere. It was, quite literally, a planetary string anchored between core and sky. 2. The plasma wave. At the same time, a joint ESA-JAXA satellite in polar orbit detected plasma wave harmonics in the ionosphere directly above the Rockies. These harmonics were phase-locked to the sky pulse but extended far beyond the upper atmosphere, reaching into the magnetosphere. The wave signature was eerily clean, a standing oscillation between Earth's ionosphere and magnetopause, driven from below rather than above. It was as though Earth's interior was striking the magnetic field like a drum. A comparison of data revealed a perfect three-phase coupling. Mantle oscillation initiated the tremor. Atmospheric resonance amplified it. Magnetospheric plasma waves carried it outward into space. 3. The solar magnetic trigger. Then came the solar event. On June 7, 2033, the Sun released a massive coronal mass ejection, CME, but unlike typical events, this one carried an unusual magnetic field orientation. Its north-south magnetic component matched the harmonic pattern previously associated with Pluto's longitudinal position. When the CME reached Earth, the sky pulse didn't merely respond, it spiked. The amplitude doubled in less than 2 hours. Low Earth orbit satellites experienced unexpected orbital decay as atmospheric density surged. Shortwave radio communications flickered. Magnetometers worldwide recorded synchronized surges. Most dramatically, the 47-minute primary mode split into 4 discrete harmonics, forming a complex chord that propagated through both mantle and magnetosphere. It was the first time scientists had observed the entire planet atmosphere space system ring like a single instrument. The breakthrough. In the midst of the chaos, an interdisciplinary team at the European Center for Geophysical Modeling integrated real-time data streams into a new class of AI-driven inverse models. Within 72 hours, the model produced a startling result. The sky pulse was not a new phenomenon. It was a long-standing natural resonance of the Earth-Sun system, triggered episodically during specific alignments of outer planetary orbits, and intensified when deep mantle structures beneath the Rockies intersected with those solar harmonics. The model suggested that the resonance had likely occurred many times in geological history, but only now, with a rapidly changing atmosphere, heightened solar activity, and sensitive instruments, had it become both detectable and disruptive. The race for stability. Governments faced a sobering reality. The sky pulse could not be turned off. It was not an external attack nor a controllable signal, but a planetary-scale interaction. The only viable response was adaptation, recalibrating satellite systems, updating atmospheric models, and building resilience against periodic surges. An emergency multinational task force drafted protocols for resonance events, coordinating power grids, aviation routes, and satellite operations. For the first time, planetary resonance forecasting joined the ranks of earthquake prediction and space weather monitoring. Scientific and cultural reckoning. The implications extended beyond engineering. Humanity had, for centuries, treated Earth as a passive stage, a world on which things happen. The sky pulse forced a paradigm shift. Earth itself was an active, resonant body, linked to solar and planetary rhythms through deep, physical structures. The Rockies, long regarded as silent witnesses to tectonic history, were revealed as an essential node in this planetary circuit. Their rise, driven by subduction and uplift, had exposed and anchored a deep mantle structure that now acted as a bridge between core, crust, sky, and space. Pluto's role, though indirect, was poetic. Its orbital position served as a marker of these deep solar harmonics, a distant metronome for a planetary song playing unnoticed for eons. The final correlation. Near the end of 2033, after months of cross-disciplinary analysis, one final discovery sealed the story. Ice cores from Greenland, reanalyzed with ultra-precise isotopic techniques, revealed periodic spikes in cosmogenic isotopes corresponding to ancient solar magnetic cycles, and subtly to the same harmonic intervals as the sky pulse. The resonance had left its fingerprints in the geological record, stretching back tens of thousands of years. Humanity had simply never recognized the pattern. Planet that sings. When the findings were announced at the International Geophysical Union meeting in Vienna, there was a rare, collective silence in the auditorium. Years of frantic investigation had distilled into a single, profound realization. Earth is not merely a planet with an atmosphere. It is a resonant system, a body that sings, in harmony and sometimes in discord, with the rhythms of the solar system. The sky pulse would not destroy the world, but it had revealed something deeper, a hidden layer of planetary behavior, as real as tectonics or climate, yet previously unheard. The story that began with ancient seas turned into mountains, with a distant icy world losing its breath, and with the fragile shell of air above us, had come full circle. Deep beneath the Rockies, the bones of the continent were still humming, a sound as old as the planet itself. Part 16 Epilogue Echoes. In the months that followed the 2033 resonance peak, the sky pulse slowly settled into a steady, measurable rhythm. The panic that had gripped space agencies and governments gave way to something far more enduring, a quiet, collective attentiveness. What once was an invisible phenomenon had become part of the background hum of civilization. Navigation satellites now include resonance corrections in their algorithms, just as they do for ionospheric delays. Atmospheric models account for the periodic thermospheric expansions triggered by the pulse. International monitoring networks track the oscillations as routinely as they track solar flares or earthquakes. Scientists refer to it simply as the pulse. A new discipline. From the storm of discovery emerged a new field, planetary resonance geophysics. It sits at the intersection of mantle dynamics, atmospheric science, magnetospheric physics, and solar astronomy. Researchers study how deep Earth structures act as resonant cavities, how solar magnetic harmonics couple with them, and how planetary positions, Pluto's among them, serve as celestial metronomes. The Rockies, once seen as the static backbone of North America, are now recognized as a key resonant node in this global system. Borehole sensors, seismic arrays, and plasma instruments are permanently stationed across Colorado and New Mexico, turning the region into a kind of planetary observatory, listening to the Earth's interior and its sky simultaneously. Historical reinterpretations. Ancient records and proxy data are being re-examined with new eyes. Ice cores, cave deposits, and even archaeological chronicles hint at periodic atmospheric and geomagnetic anomalies that coincide with past resonance peaks. Some historians note curious reports of strange winds, sky tremors, or lights in the firmament that align with known solar cycles. What was once myth and mystery may, in part, have been humanity's unconscious witnessing of Earth's deep rhythmic behavior. the distant metronome. Pluto's orbital path, still slowly tracing its elongated ellipse beyond Neptune, continues to align with the same heliocentric longitudes that marked previous resonance events. While no causal influence emanates from the distant dwarf planet, its position remains a reliable celestial clock, a marker of the deeper solar harmonic cycles that shape these planetary resonances. Every 248 years, when Pluto swings through its perihelion arc, scientists now watch for the buildup of subtle patterns in the mantle and magnetosphere. What was once coincidence is now forecasting. Unanswered questions. Despite the breakthrough, many mysteries remain. Why does the mantle column beneath the Rockies act as the planet's most sensitive resonant cavity? How stable is this resonance over geologic time? Could it ever destabilize or fade? Does Earth's changing climate amplify or dampen the pulse? And most tantalizingly, are similar resonant nodes hidden beneath other continents, waiting to be detected? Teams are already deploying instruments to Africa's Rift Valley, the Andes, and the Siberian platform, searching for other strings in the planetary instrument. A subtle shift. Amid this new era of observation, something unexpected is happening in public culture. Once the sky pulse entered the collective imagination, artists, musicians, and writers began incorporating its rhythm into their work. Concerts synchronize light and sound to the real-time oscillation data. Poets compare it to the planet's breath. For the first time, humanity is not just measuring Earth's hidden rhythms. It is listening to them. Final scene. In a control room outside Boulder, Colorado, a cluster of plasma wave monitors hum softly. Their digital displays trace a precise sinusoidal curve, the heartbeat of a planet. A technician checks the readings one last time before leaving for the night. Everything looks normal. Amplitude stable, frequency steady, harmonic modes in balance. She switches off the overhead lights. On the monitor, as the room darkens, a new, faint harmonic trace flickers for the briefest moment. It's offset from the main pulse, higher frequency, unfamiliar phase. She doesn't see it. The screen steadies again. The pulse continues, and outside, the wind moves across the Rockies, where deep beneath the crust, the Earth's hidden cord still vibrates, quietly, endlessly, waiting.